Hello, Chemistry 11. This is Mr. Chan. And today's lesson, we're going to do a little bit of review of grade stuff that you learned back in grade 10. So if you missed the class, the assignment for this particular class would have been the front page of the handout that I gave you. And the first thing that I would like you to do is I would like you to complete the table. Now, so what you have is you have Dalton, Thompson, and Rutherford. Now, this you should have been familiar with back in grade 10, but what I wanted you to do was just a quick review. So when you read those sections, what is the Dalton's idea of the atom? So let's say if I were to draw just a sample of this as an example, let's just say his idea of the atom was a happy face. You read on, and let's say you read the Thomson model. So what you have is here. So you have a happy face. Okay. So what you would say is difference from the previous theory. So let's say it has a hair. But similarities is that it is still a happy face. Okay. Rutherford, you might have something like this. Okay. So again, what's the difference? Now it has a body, but it's still a happy face. And it still has hair. Okay. So that's how I would like you to fill in the table. And you get the information based upon the readings from pages 221 to 222 and pages 229 to 233 in your textbook. As well, what I would like you to do is complete page 233, the review and practice on page 233, numbers 3 and 4. Now, the second part of the lesson is definitely a review of Science 10. So some things that you should remember from Science 10 is, let's say, the vocabulary of the atomic number. So the atomic number is the number of protons in the nucleus of the element. Now, another name for this is called the nuclear charge. Now, one thing about the atomic number is that it defines the element and does not change. It never changes. So the number of protons for a specific element, let's say carbon is 7. Oh, sorry, carbon is 6. So all atoms of carbon will have 6 protons. And that's why it has the atomic number of 6. If it were to increase the number of protons, then the element will change. And in this case, if we added one more, it would be nitrogen. Okay. So for a neutral element called atoms, the number of protons equals the number of electrons. In other words, if we take the difference between the number of protons and electrons, it would be 0. So for a neutral element, how do we know it's an element? We call it atoms. Okay, so let's say, for example, let's say we had sodium atom. Now, the key word here is atom. And so what that means is that it is neutral. So if we look on the periodic table and we look for sodium, which is the neutral atom, then what we have is sodium would have the number of protons would equal 11, and the number of electrons is also 11. Notice these are the same. And because they're the same number, this is why it's considered neutral. Now, another thing that you should have remembered from Science 10 is atomic mass. So atomic mass is the number of protons plus the number of neutrons. Okay, now why aren't electrons included in the atomic mass? It's because the electrons are so small, its relative mass is considered insignificant. Okay, it's like your hair. Let's say if you wanted to lose weight, you cut off your hair. Yes, you lose a little bit of weight, but because your hair is so insignificant, it doesn't make a big deal. Now, generally, one can write elements like this. Okay, now this way that I write it, this is called, if you remember, it's called standard notation. So in this case, what happens? So let's say we had this little number here. Okay, so the 39 on the upper left, this would be the atomic mass. Down here on the bottom little number here, this would be the atomic number. And on the upper right-hand corner, in this case, this would be the charge. Okay. Now, one thing you will notice is that in this case, I did not write the atomic number. In some books, for the standard notation, they would put the atomic number in. Now, in this particular case, it is optional because for the element of potassium, potassium has the symbol of K. Its atomic number is 19. So that means it has 19 protons. So in some places where if you write the 19, it's kind of redundant. So in this particular case, if you remember back in grade 10, the number of protons would be 19. The number of electrons would also be 19. How do I know that? Is because notice there's no charge. And the number of neutrons in this case would be equal to 20. How did we get that? Is we took the atomic mass, subtracted the atomic number, and that leaves us with the number of 20 for neutrons. Now, remember, another term is ions. It's an element that has either gained or lost electrons, and therefore has an overall charge. Okay, so let's say, for example, so in this case, sodium +1. So if we said sodium ion, the ion here means that it has a charge. So in this case, the sodium ion would be Na+1. Notice the +1 here, it has a charge. So if we were to do the number of protons, number of electrons, number of neutrons, number of protons never changes, so that's 11. Number of electrons is 10. Number of neutrons is 12. Notice these two numbers are different. And that is why it has a charge. Okay. Now, I'm going through this fairly quickly because you should have remembered this back in grade 10. All right. Now, another thing you should have remembered from grade 10 is the term isotopes. It is atoms with the same element but with different number of neutrons. Okay, so let's say we have the symbol chlorine-35 and chlorine-37. What does that mean? So this chlorine-35, it means that it's the element chlorine with a mass of 35 versus chlorine-37. Let's see. In this case, chlorine-37 is still the element chlorine, doesn't change, but in this case, with a mass of 37. Now, again, why does it have a different mass? Is because between the 35 to 37, what you have is different number of neutrons. Okay. Now, some of you may have used this last year, the PhET simulation, or even in grade 9. Let me see here. Let's see. You probably did this one here. And so with isotopes, you have hydrogen 1. So that means a hydrogen with a mass of 1. When I added a neutron, notice the hydrogen element still stays the same, but now the mass is changed to 2. Now we have hydrogen 3. Still hydrogen, which is 1 proton, but now we have 2 neutrons. That's why the mass is changed to 3. Now, it's been theorized that the neutrons are there to provide stability for the atom. Okay, so the more number of protons there is, the more neutrons are needed to maintain the stability. But if there isn't a right ratio, then the atom becomes unstable. Okay. Now, why aren't atomic masses whole numbers? If you look at your periodic table, let's see here, periodic table. Now, you notice that, let's say for oxygen, how come it's 15.9994? Or chlorine, if we erase this here, how come it's 35.4527? You know, how can you have 0.4527 of a neutron? And so as a result, what happens is when calculating the average atomic masses, we need to take into consideration all the isotopes that are available for the element. Now, on page 237 in your textbook, what you will see is you'll see a page like this. So what we have is we have 2 isotopes of chlorine, chlorine-35 and chlorine-37. Now, if you take a look at across the top, it says, what is the abundance in nature? So there's approximately 75.77% of chlorine-35 in nature and about 24.23% of chlorine-37 in nature. So when we calculate the atomic masses, we have to take all of them into consideration. For example, if I were to say, what is the average age of the students in the class, I need to take everybody who's 15, 16, and 17 and take their ages into consideration. So that is the same idea. So how do we do the calculation? So in this case, it says calculate the average atomic mass of chlorine. So what do we do? So we take the mass of chlorine-35 times the percent of chlorine 35 plus we take the mass of chlorine 37 times the percent of chlorine 37. Now, the only reason why we only did this twice is because there's only 2 isotopes of chlorine. But if we had something like, oh, I don't know, look at oxygen. There are 3 types of isotopes of oxygen, then we need to do all 3. Okay? So in this case, what do we do? So the mass of chlorine 35, in this case, is 35 times the percentage of chlorine 35, which is 0.7577. I just changed the percentage to a decimal, plus the mass of chlorine 37, which is 37, times the percent abundance, which is 0.2423. And so if we were to add all of this up, we have 35 times 0.7577 plus 37 times 0.2423. I get an answer of approximately 35.485. Now, again, there's experimental uncertainty. So that's why your chlorine, this doesn't match up exactly with the atomic mass that's on your periodic table. Okay. Now, how do they get this percent abundance? How do they know this? Well, they use something called a mass spectrometer or mass spectrophotometer. One can produce a spectrum whose information can be interpreted. So what happens is this. A mass spectrometer looks something like this. So we throw an element into a machine. Okay, well, let me just rewrite this. So we have our element. Now, and what we do is we subject that element to a magnetic field. And that magnetic field will bend the elements and break them apart into their individual isotopes, because the different isotopes have different masses and they will be bent different ways. Let me show you what I mean by this. So let's say we have it here. Okay, so let's say if you look up here, let's look at an element mass of 1 kilogram. Let's say the speed we don't change, and let's put a magnetic field. Okay, now if we play this, the element is firing, and notice it gets bent into this magnetic field. So it is about 1.3 meters, hypothetically. Now, let's do 2 kilograms, and let's restart the simulation. So because the mass is heavier, notice it takes a longer bend. Now it's 2.7 meters and even heavier. Let's restart it and then notice what happens. Notice it takes even more time for the element to bend. It's 4 meters. So in this case, depending on the mass, the amount of bending could be more or less. And what happens is this bending will result in a little what we call graph here, a spectrograph. Now, what happens is we have the number of atoms and the relative mass of each of the isotopes of the element. Okay, so what you need to be aware of is you need to know how to read this. Know how to read it. So if we were to look at this, we would know for this particular element, because 202 is the highest peak, the majority of the isotopes are with atomic mass of 202. If we take a look, it has the highest peak. So this is, let's say 30. The second most abundant isotope would be 200. So this is how you would read that particular graph. All right. Now that is the lesson that we had talked about last day. So hopefully, if you missed the class, you can use this to help you catch up. All right, folks. Thank you very much. Have a good day. Bye-bye.